What if getting good at data structures and algorithms wasn't really about memorizing a bunch of code? What if it was more about learning to think like a scientist? Well, today we're going to try to flip the script on this whole topic and see how we can go from staring at a frustrating puzzle to really understanding a powerful principle for solving problems. So let's just dive right in with a classic challenge. Okay, here it is. It's a famous problem called two-sum. You've got a list of numbers and you've got a target number. In this case, it's 9. The job is simple. Just find the two numbers in that list that add up to 9 and tell me where they are, what their positions or indices are. Before we go any further, just take a second. How would you solve this? All right, the first thing that probably pops into your head is what we call the brute force method. You just check everything. You grab the first number, 2, and then you just add it to every other number in the list, one by one. So does 2 plus 7 equal 9? Yep, it does. We found it on the very first try. They're at index 0 and index 1. Super simple, and hey, it gets the job done. But, and this is the question that's at the heart of, well, all of computer science, it works, sure, but is it any good? I mean, what if that list had a million numbers in it? Checking every single possible pair would take forever. So we have to ask ourselves that crucial question: can we do better? And the answer to that question almost always comes down to using the right tool. In programming, our tools for organizing information are called data structures. You can think of them like specialized containers. Each one is designed to do certain jobs, like searching for something really, really well. And for this particular problem, our much smarter tool is a data structure called a hash map. It's basically built for situations where you need to look things up in a snap. But look, let's forget the fancy term for a second. Let's make this really simple. Just imagine you have a little notebook next to you. And as we go through our list of numbers, we're just going to jot down 2 things in that notebook: the number we just saw and where we saw it. That's it. Okay, let's walk through it with our notebook. We look at the first number. It's a 2. Now, to get to our target of 9, what number are we looking for? A 7, right? So we peek into our notebook. Is 7 in there? Nope, the notebook is empty. So we just make a quick note. I saw the number 2 at index 0. Cool. Now we move on. The next number is 7. Okay, to get to 9, what do we need? We need a 2. Let's check the notebook. And bingo, there it is. Our note says we already saw a 2 at index 0. We found our pair. Do you see the difference? It was amazing. We just went through the list one time. We never had to circle back, never had to recheck anything. It was just one smooth, clean pass. So it feels a whole lot faster, doesn't it? But in this field, a feeling isn't good enough. How do we actually prove it? How do we measure this improvement in a more scientific way? Answering this is what takes us from just writing code to really doing computer science. It turns out both of our approaches, the clunky brute force way and our clever notebook way, have a formal name. They're both considered algorithms. An algorithm is really just a fancy word for a recipe. It's a clear list of steps that takes some input and gives you a specific output. And to compare these recipes, to see which one's better, we analyze something called time complexity. Now, this isn't about timing things with a stopwatch. It's about counting the number of operations the algorithm has to do as our input list, let's call it size n, gets bigger and bigger and bigger. And the special language we use for this is called Big O notation. Now, I know it can look a little intimidating with O and the parentheses, but the idea behind it is actually pretty simple. All it does is describe how fast the runtime grows. Does it grow nice and steady, or does it just explode as our list gets longer? So let's put our 2 methods head to head. The brute force method, that's O of n squared. That means if you double the size of your list, the work quadruples. If you 10x the list, the work goes up 100x. It gets slow really fast. But our hash map method is O of n, or linear. If you double the list, the work just doubles. It scales beautifully. But look closely, there's a trade-off. To get that amazing speed, we had to use some extra memory for our notebook. And this right here, this is the whole game. This is the core idea. We made a trade. We used a little bit of extra memory, some space, to get a massive improvement in speed, or time. This concept of a time-space trade-off is honestly one of the most fundamental ideas in all of programming. Which brings us to the real point of all this. Learning data structures and algorithms isn't about memorizing solutions to 100 different problems. It's about developing a mindset where you don't just solve a problem, you analyze it. So what does that look like? Well, an effective problem solver always does these things. First, they make absolutely sure their solution actually works. Then they analyze it. They think about both time and space. They pick their tools, their data structures, on purpose, not just by accident. And maybe most important of all, they can clearly explain why they made their choices and what the trade-offs were. This quote just says it all perfectly. The goal shifts. It's not about just finding an answer that spits out the right result anymore. The real goal is to find a good answer and then be able to stand behind it and justify why it's good. And the coolest part is that this whole notebook pattern we just learned, using a hash map to remember things we've seen, is a building block for solving so many other problems. Things like counting how many times a character appears in a string, or analyzing a stream of data with something called a sliding window. It's the same idea, over and over again. Okay, so you're probably thinking, this is great, but where do I go from here? How do you actually take this new mindset and turn it into a real, practical skill? Well, here's a little roadmap for you. First, go back and master TwoSum. I mean, really master it. Then, try a version of it where the list is already sorted. Does that change things? After that, try a problem called valid anagram, which uses the exact same hash map idea for counting things. And finally, check out valid parentheses, which will introduce you to another powerhouse data structure, the stack. So, I want you to leave with this thought. The ultimate question is never what's the right answer. It's what is the best trade-off for this specific situation. The next time you're tackling a problem, don't just hunt for a solution. Hunt for the trade-offs. Are you willing to spend a little memory to gain a whole lot of speed? Answering that question, that's what great engineering is all about.